All right, folks, this is for the Centripetal Force Lab. We have this set up here. The diagram is in the lab manual, or the handout that I gave you. This setup here is set up such that we are able to hang some masses off to the left here. Right now, currently, there's a 50-gram hanger that's on there. The issues, of course, we have the hanging mass here and the pointer here. These two have to be lined up. So the bottom of the hanger, bottom of the hanging mass and the top of this little pin here have to line up. This is what we're trying to achieve here by hanging a bunch of masses off to the left. How much force is required to pull it out to that point there, which we call the equilibrium position. And so we're going to go ahead and do that. This is already 50 grams here. So we'll add some masses onto this side. This is 100, so it's 150, 250, 350, 450, looks like it's almost there, 450, and then see if this works. No, that's too much. 550 is too much. So 450, and then we have to add some additional masses on here. 450 and then 50. Nope, too much.
Too much. Just a small amount.
455.
That looks good.
460.
It's good.
Pretty close.
Look on the camera.
Yeah. 460. 470. All right, looks like there's 470 grams there. That'll be fine. All right, so the hanging mass is 470 grams. That's 0.470 kilograms. That 0 is a significant figure, so you have to keep that in mind. 0.470 kilograms. Now you have to multiply that by 9.8 meters per second squared to get newtons. So that's the amount of force that is required to pull the system out to equilibrium position. Now what we do, and this is the hard part, is we have to remove the paper clip and the masses and such to spin this system around so that it reaches equilibrium. So now we remove this the force over here, and so now this thing gets pulled inwards like that. But the way we want to get this to come out now is by spinning the system. And this is the hard part because I have to eyeball the bottom of this, the mass here with the top of the pin here, rotating it at the right speed here, all right? Now, you're gonna have to do this with your stopwatch at home. I'm gonna be spinning this thing, all right? You're gonna be keeping track of this stuff here with your thing. And I'll try to make sure that you count, I think the number was like 30 rotations for the system, all right? And so, all right, so here we go. Oh, by the way, you'll need this measurement here. The length of this thing from the axis to this post over here is, according to our ruler here, is about 17 centimeters. And so 17 centimeters or 0.17 meters is what you'll use for R for that case, all right? And so the mass of this thing is, oh, geez, 430, I can't read it anymore. Oh no. We'll have to measure that later, all right? 450 something.
Yeah.
Yeah, I don't know, I can't read it. We'll get that mass later, all right? So let's go ahead and spin this up. Well, not yet, because it's got to spin at the right speed here. Gotta make sure I keep my head down for this. Hard to do this while getting out of frame here. You have to just basically keep in mind here. All right, I'll spin it. I guess my head's going to be in the way, unfortunately, but I'll spin it at the right rate here. So I'll count down from 3 to 0, and then you can start your stopwatch at 0. 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All right? So using the radius here, multiplying that by 2 pi, you'll get the circumference. And using the circumference and the time that we measured for 30 rotations, you can get a rotation, a time for one rotation by dividing by 30, using your stopwatch measurement. So the time that you took for 30 rotations, divide by 30 to get one rotation, right? So 2 pi r divided by t, which is the time it took for one complete cycle around. That should get you your speed, all right? And again, r should be measured in meters. So it's 0.17 meters multiplied by 2 pi divided by the time it took to go around once, okay? That will, you can use that to calculate your v, your speed. If you remember, the formula for centripetal force is mass times speed squared divided by r, all right? And so we have the mass of this thing, which we have yet to measure, the speed, which is something you calculate 2 pi r divided by capital T, the period of one rotation, and then the whole thing divided by r, which is the thing we measured here, all right? So very quickly, I'm going to take this off and run it over to the scale, and I'll shout it out. All right, I'll be right back.
How many seconds? 24?
24.72, yeah, about 24.
All right. The mass is 457.11 grams, 457.11 grams, or 0.45711 kilograms, all right? So that should be enough information for you to calculate the centripetal force, the force associated with the rotation here, that's, you know, of the spring pulling inwards on the system as you rotate this thing outwards. That should be comparable to the amount of force that was required by the hanging mass over here in part 1, pulling it outwards to here. You compare those two values of the centripetal force with the hanging mass force, and they should be within 10% of each other. That's the scope of the lab today, all right? This is to verify that centripetal force is, given by the formula mv squared divided by r, all right? Thank you.